Abram sir, can you hear me?
This meeting is being recorded.
Hello sir. Abram, can you hear me?
Yes,
Sir, Abram sir, I am Sanuj B. Can you hear me?
yes, I can hear.
Can I continue my presentation after one more participant? Or?
After the next one.
Okay, sir. Thank you.
The next participant is CP21 Rose Pole. Are you there? Hello, Sunil sir.
Yes, sir. Yes, sir.
So,
Can I share my screen now?
yes.
Okay, sir. Sir, is my screen visible?
Yes, yes.
Okay. So good afternoon to all of you. My presentation is on Linear-chaotic eigenset of direct sum of linear operators. Outline of the presentation is like this: introduction, research problems, notations, definitions and preliminaries, and our results with theorem 1, 2, 3, 4, conclusion and reference. Introduction. The notion of Linear-chaos in a topological dynamic system was first used by T.Y. Lee and J. York in their paper, Period 3 implies chaos. There are several other types of chaos available in literature: Devani chaos, distributional chaos, Bruckner-Seder chaos, Wiggins chaos, etc. are some of them. Relationship between these chaos are analyzed by several researchers. For example, Huang and A has shown that Devani's chaos implies Linear chaos. Research work has been carried out in the areas of Linear chaos and Devani chaos in linear dynamics also. The introduction of irregular vectors make it possible to bring Linear chaos in linear dynamic setting, whereas hypercyclic vectors and denseness of periodic points brings chaos in the sense of Devani. The Linear-chaotic eigenset of a bounded linear operator has recently been introduced in our own paper and found that Linear-chaotic eigenset of a positive integer multiple of backward shift operator on L2n is a disk in the complex plane. In this paper, we will be concerned with Linear-chaotic eigenset of the direct sum of linear operators, compact, normal, and self-adjoint operators. Our research problems: identify the Linear-chaotic eigenset of the direct sum of linear operators, find the Linear-chaotic eigenset of compact operators, find the Linear-chaotic eigenset of normal operators, find the Linear-chaotic eigenset of self-adjoint operators. Some notations are using in this presentation. T, it is the unit disk, unit circle. D, unit disk. X, an infinite dimensional separable complex Banach space. B of X, the space of all bounded linear operators on X. H, an infinite dimensional separable complex Hilbert space. And B of H, the space of all bounded linear operators on H. Chaos in the sense of Devani. The f from X to X is a continuous map acting on some metric space XD. The map F is said to be Devani chaotic if F is topologically transitive, F has dense set of periodic points, F has a sensitive dependence on initial conditions. Sensitive dependence on initial conditions means there exists delta positive such that for any x in X and every neighborhood U of X, one can find Y element of U and an integer n greater than or equal to 0 such that the distance between Fn of X, Fn y greater than or equal to delta. Then Linear chaos. That F from X to X is continuous map acting on some metric space XD. The set xy is said to be Linear chaotic pair if limit supreme of distance between Fn of X and Fn y greater than 0 at the same time limit infimum of dfn of X, Fn y is equal to 0. So a subset gamma of X is called a scrambled set if each pair of two distinct points in gamma is a Linear chaotic pair. Relationship between Devani chaos and Linear chaos. F from X to X be continuous map acting on some metric space XD. The map F is said to be Linear chaotic if there exists an uncountable scrambled set. In the reference number 12 given in F is Devani chaotic can be proved as Linear chaotic. This is proved by the authors in 12, reference 12. In irregular vectors, let T belongs to V of X. An irregular vector for an operator T is an X element of X that's such that limit supreme of norm Tnx is equal to infinity and limit infimum of norm Tnx is equal to 0. some of the properties of irregular vectors. X is an irregular vector of t if and only if there are two sequences kn and ln increasing to infinity such that limit of t kn x is equal to 0 and limit of norm t ln x is equal to infinity. This one first property is required in our results. So the rest is I am skipping. Some relation between Liouville kites and irregular vectors. Let T from X to X be an operator. The following assertions are equivalent. T is Liouville-chaotic implies T admits a Liouville pair implies T admits an irregular vector. Then corollary, let T from X to X be a Liouville-chaotic pair operator. Then following assertions hold. The spectrum of T intersection the boundary of D is non-empty. T raised to n is Liouville-chaotic for every n element of n. T is not compact. T is not normal. Then some of the results of properties of Liouville-chaotic operators. Come to the definition of Liouville-chaotic eigenset. For T belongs to V of X, the Liouville-chaotic eigenset of T denoted by Lyt is defined by Lyt is equal to set of all lambda element of C such that T minus lambda is Liouville-chaotic. This definition is given by one of the paper of our own. Then this theorem, Liouville-chaotic eigenset of the positive multiple of backward shift operator is proved as n plus 1 D, and the union of such Ly and T is proved as C. Then come to direct sum of linear operators. Let Xn n greater than or equal to be countable collection of separable Banach space. The direct sum of space Xn is defined as the set of all Xn's with the Xn element of Xn. Then similarly, the direct sum of operators is also defined. Then some remarks. T1 direct sum T2 is of X1 X2 is same as T1 of X1 T2 X2. T1 direct sum T2 square of X1 X2 is the pair T1 square X1 T2 X square. We can generalize into up to of index n. Then our results. The first theorem, if T1 T2 belongs to Bx, then Ly of T1 direct sum T2 is equal to Ly of T1 union Ly of T2. An outline of the proof is given like this. Assume that the T1 direct sum T2 minus lambda is Liouville-chaotic and Xy is an irregular vector for T1 plus T2 minus lambda I. By applying some for the first property of irregular vectors, we can get the equation number 1 and 2, and by using the equation 1 and 2, the definition gives that x is an irregular vector for T1 minus lambda I and y is an irregular vector for T2 minus lambda I. From this, we have established our result. In second result, let T be a compact operator, then Lyt is always a subset of T, the circle. The example of such a situation is given like from the literature, weighted shift operator, backward shift operator. Then another result, let T belongs to be a normal operator, then Lyt is proved as the empty set. The idea is like this. Consider T minus lambda star T minus lambda, and can be easily shown that T minus lambda into T minus lambda shows that it is normal. By the previous result, T minus lambda is not Liouville-chaotic, hence by definition given in our own paper, Lyt is equal to null set. Then last one, the T belongs to BH is a self-adjoint operator, then Lyt is equal to 5. So it is easily observed that every self-adjoint operators are normal, and from according to the previous result, it is applied here. So the result is again easily proved. So these are the concluding remarks. We proved that Liouville-chaotic eigenset of T1 plus T2 direct sum is exactly same as Liouville-chaotic eigenset of T1 and T2. Proved that Liouville-chaotic eigenset of compact operator is always subset of unit circle. We proved that Liouville-chaotic eigenset of a normal operator on complex Hilbert space is always empty. We proved that Liouville-chaotic eigenset of self-adjoint operators on complex cell is always empty. So these are the references we have used. Thank you.
Okay, sir. Any queries? Okay, thank you, sir.
Thank you.
Okay. Next participant, CP21, row 4. Please share your slides. Can you hear me? Hello. Please unmute. Let me say unmute.
Unmute idu. Hello.
Okay, miss. I can hear.
Hello.
Please share your slides. Please share your slides. Can you hear me?
Hello.
Hello. Can you
Yes,
hear?
sir. Yes, sir. Yes, sir.
Can you share your slides?
Okay, sir. Okay, sir. I shall.
Okay, you can start.
Good afternoon. Myself is Rose Paul, Research Scholar, Department of Mathematics, St. Thomas College, Autonomous Thrissur. I'm doing my research under the guidance of Dr. Sister Julie Andrews, Assistant Professor, Department of Mathematics, St. Thomas College, Thrissur. Here, I'm going to present a paper on a study on the thermal and physical properties of titania water and alumina water nanofluids. The content of my presentation is objective, introduction, mathematical formulation, results and discussion, references. The objective of this paper is to study about the thermophysical properties such as specific heat capacity, density, dynamic viscosity, Prandtl number, and effective thermal conductivity of titania water or titanium dioxide water, nanofluid, and alumina water or aluminium dioxide water, aluminium oxide water nanofluids for a given volume fraction. Introduction. And nowadays, cooling becomes one of the top technical challenges facing high-tech industries such as microelectronics, transportation, and manufacturing. Now, new technologies and new advanced fluids with the potential to improve flow and thermal characteristics are of critical importance. Nanofluids are promising to meet and enhance the challenges. Nanofluid is a suspension of solid nanoparticles 1 to 100 nanometer diameter in conventional liquids like water, oil, or ethylene glycol. These fluids are engineered colloidal suspensions of nanoparticles in a base fluid. Nanoparticles used in nanofluids have been made of various materials such as oxide ceramics, nitride ceramics, carbide ceramics, metals, semiconductors, carbon nanotubes, composite metals such as alloy nanoparticles, etc. Now the mathematical formulation. Here in my study, I have taken two nanofluids. So one is titania water nanofluid and the other one is alumina water nanofluid. In this study of the thermal and physical properties of titania water and alumina water nanofluids we consider, and by considering the base fluid as water with a Prandtl number 7.02. In the base temperature 293 Kelvin, and solid spherical titania and alumina nanoparticles of 100 nanometer diameter mixed with water has been considered as the nanofluid. The density, specific heat capacity, effective thermal conductivity, dynamic viscosity, and the Prandtl number of the nanofluid depends on the volume fraction phi of the nanoparticles used. Volume fraction means the quantity of solid particle in 100 cc of the fluid. the base properties of the physical properties of the base fluid water, titanium dioxide and aluminum oxide at it's not a 200 degree, this is 20 degrees Celsius or 293 Kelvin R. For water, the density is 1000.52 and the specific heat is 4181.8 and the thermal conductivity is 0.597. And for the aluminum oxide, it is 3970 the density and the specific heat is 769 and the thermal conductivity is 36. And titanium dioxide, it is the density is 4240 and the specific heat is 683 and thermal conductivity is 8.9538. And the effective density is rho NF of titanium dioxide water and aluminum oxide water nanofluid is given by the formula rho NF is equal to 1 minus 5 rho F plus rho into rho S, where rho S is the density of the fluid and rho S is the density of the solid particles. Now from the figure, it shows that when the volume fraction I have taken from 0 to 0.1, when the volume fraction increases, density of both the nanofluids increases, and the increase is more for titanium water nanofluid than alumina water nanofluid. Next is the specific heat capacity CPNF of titanium water and alumina water nanofluids are given by the relation CPNF is equal to 1 minus 5 CPF plus 5 CPS, where CPS is the specific heat capacity of the base fluid and CPS is the specific heat capacity of the solid particle. And from the graph, it shows that when the volume fraction increases, the specific heat capacity of both the nanofluids are decreases, and the alumina water nanofluid and titanium water nanofluid almost have the same specific heat capacity. Next is the effective thermal conductivity. It is denoted by KNF and given by the formula KNF is equal to KF into KS by KF plus N minus 1 minus N minus 1 5 into 1 minus KS by KF divided by KS by KF plus N minus 1 plus 5 into 1 minus KS by KF. And here N is 3 by psi, and since I have considered I have taken as the spherical solid particles, so for the spherical solid particle the psi is 1, so N is 3 and Kf is the thermal conductivity of the fluid and Ks is the thermal conductivity of the solid particles. When the volume fraction increases, the effective thermal conductivity of both the nanofluids increases, and the alumina water nanofluid has more thermal conductivity than the titanium water nanofluid. Next is the dynamic viscosity. It is denoted by mu NF and given by the relation mu NF is equal to mu F divided by 1 minus 5 raised to 2.5. Where mu F is the viscosity of the base fluid. Here I have taken the base fluid as water in 20 degrees Celsius and the viscosity is 0.001002 eta per ns dot m raised to minus 2. And from this graph, it shows that even though the volume fraction increases in both the nanofluids, viscosity is also increases, but both have the same viscosity. So this viscosity is not depends upon the solid particles we are using. Next is the Prandtl number. Prandtl number is the ratio between the momentum diffusivity to the thermal diffusivity. And the Prandtl number PR of the nanofluid is denoted by PRNF, where PRNF is equal to KF into mu NF CPNF divided by KNF. KF is the thermal conductivity of the base fluid and mu NF is the viscosity of the nanofluid, and the CPNF is the specific heat capacity of the nanofluid. And from the graph, it shows that when the volume fraction increases, the Prandtl number decreases, and the titanium water nanofluid have more Prandtl number. than the alumina water nanofluid. And the results and conclude discussion. When the volume fraction increases, density of both titanium water and alumina water nanofluids increases, and the increase is more for titanium water nanofluid than alumina water nanofluids. When the volume fraction increases, heat capacity of both the nanofluids decreases. Also, alumina water nanofluid and titanium water nanofluid have almost same specific heat capacity. The effective thermal conductivity of both the nanofluids increases with the increase of volume fraction phi. The thermal conductivity of alumina water nanofluid is more than the titanium water nanofluid. And in viscosity, no change in viscosity for both the nanofluids as the volume fraction increases. But the viscosity increases for both the nanofluids. Now, when the volume fraction increases, the Prandtl number decreases in both the alumina water and titanium water nanofluids. So these are some of the thermal physical properties of, I compared just to the thermal physical properties of alumina water and the titanium water nanofluids. And these are some of my references. Thank you.
Okay, ma'am, any queries? No queries? Okay, ma'am, thank you.
Thank you, sir.
Okay. And today's contributory session 4 is over. And there is an announcement. Tomorrow's contributory session 5 and 6 start at 8:55 a.m. Okay, thank you.